hope you enjoyed this simple celebration of my 1000th video on YouTube. Hello there, viewers! This is your host, Ricky Klein, the CassetteMaster, once again. And today I want to show you a device. This is not a tape recorder, as most of my videos are about, nor is it a mechanical pencil. This is my latest project. It is a very interesting device that performs a very specific function. This is called the EPROM player / address finder. It's a semi-portable unit. As you can probably see, it has a 0 insertion force socket with an EPROM chip on it. It has 7 segment displays that are continuing to increment. It has a knob right here. We'll show what that knob does and what these buttons and switches do, and what all the knobs on the side do as well. You'll also see what looks like a parallel port on the side, although this is not a computer pinout for a parallel port. It's just a DB25 connector used according to my own design. But anyway, I will be showing you this project. It's a very fun project, which will be able to be expanded and connected to other projects in the future through the port on the side. Let's give an overview of what this device really does, what its purpose is. Now, some might think that it's a homemade EPROM programmer well, it's obviously what it really is, I'm sure, but still, at first glance, one might see it's got a ZIF socket for EPROMs, and it has what looks like a parallel port on the side. So they would probably deduce that it must be a homemade EPROM programmer. I already have 4 EPROM programmers. I have little reason to build my own EPROM programmer. This is not an EPROM programmer. Well, then what is it if it uses EPROMs? EPROM player should give you the clue. It plays sound from EPROMs. PCM, of course, or pulse code modulation. You can select a variety of different EPROMs from the 2716 all the way to the 27C010. I mean 080. The 080 is 8 megabits or 1 megabytes. The 2716 is 16 kilobits or 2 kilobytes. What we have on here is just a 2716, which in order to get 1 second of audio you need a sampling rate of 2 kilohertz, which isn't very much at all. We turn it on. You'll hear the word microchip is repeated. Now, this knob here can be used to adjust the clock frequency. Or we can make it super fast. Sounds kind of like a fast forward on a tape recorder. Now, what if we want to hear microchip in reverse? What if we only want to do it one time? There are 2 buttons right here. This button you hold down to play, and the other button is reset. Now you might notice something. All zeros are on the display. And whenever I play it, it's incremented. This display shows a hexadecimal address on the EPROM. Now, 5 digits means I can account for 20 bits worth of addresses, which is the amount of addresses you have on the maximum size EPROM this will support, the 27C080, or the 1 megabyte EPROM. However, knowing that means if I keep this playing over and over again, the counter was going to keep on going in all the digits. So if you want to have a precise address, you got to reset it first and play to whatever portion of the chip you want. The idea of showing the addresses live here is that this can be used as an address finder. In the future, I plan to make some projects such as a talking thermometer, which I know have taken forever to get around to doing, and a speech synthesizer. The speech synthesizer, I'm planning on having recordings of my voice of all the allophones, which can then be concatenated together. For the talking thermometer, I will just concatenate together pre-recorded speech samples saying various numbers, degrees, and one of 3 different units of temperature that you could select. Yes, I will include kelvins. Whenever I thought I'm going to start doing some work for that talking thermometer, I thought to myself, I'm going to need to build an address finder, and I had built one in the past when I was working on the talking clock project back in 2015. Of course, I originally was going to use PCM audio on the talking clock instead of linear predictive coded speech synthesis voice. So I had built a temporary address finder on breadboard. Well, thinking to myself that I want to have an EPROM player permanently built, I thought, well, I'll just build an EPROM player / address finder, and then through the port on the side, since the counters I'm using are up-down counters that are also presettable, I figure I would also put a port on the side in which I could have external data coming in to control the address lines separate from the counters if I wanted to. That way, I could not only find the starting and stopping addresses of all the different speech samples that I would use, but I would also be able to later on have a microcontroller and a talking thermometer control the address lines through the port. And of course, being presettable counters, if you put it into load mode, you'll basically just make the data lines of the chip transparent, so whatever goes in the port, it will be the address you go to. I could just make the talking thermometer a peripheral device that you hook up to this, and it would talk through here provided you had the right EPROM. And same would be for the speech synthesizer. A different EPROM would be used for that, a different project. I can play sound from EPROMs for fun at all kinds of different sampling rates, but I could also find starting and stopping addresses, and I could also hook up future projects to this and use it as a special device to make sound. Now, you might be wondering what all the knobs on the side do. This one down here selects the EPROM that you want to use, because some of them have different pins used for power depending on how many pins the chip has, and different pins are sometimes used for addressing, sometimes used for other things. So I wanted to be able to select the EPROM with that knob. So 2716 is option 1, and then this top knob obviously is volume. But you'll notice there's a lot of aliasing in the sound. So on the side, I have 2 controls for low pass filter. It's a Salon key design I found online, which was, I believe, a 3rd order low pass filter, but whenever I was putting some values in an online calculator, I only had 2 critical frequencies, and I wanted to be able to control each critical frequency I was thinking originally I would use one double ganged pot, but I found one pot needed to be a lot larger resistance value than the other, so I ended up using two separate pots to control two critical frequencies of a Salon key or Salon key filter. That way I can reduce the aliasing. Now let's have some fun with the address finder and try some different chips. You've heard an example of extremely low sound quality, sampling rate of only 2 kHz. Here I have a chip whose sampling rate is, matter of fact, even larger than 44.1 kHz. I don't remember exactly what it was, but I think it was 50 something kHz. Of course, we have to set it to the right chip. This one is a 2 megabyte chip. It sounds like you're hearing a horrible, horrible monster. You can see the difference between the sampling rates is quite apparent with the sound.
EPROM. I'm here to see how this system works. I'm Anthony EPROM. I'm here to see how this system works.
The last address of this chip is 3FFFF. That's pretty close. Obviously, of course, you can go over 4 and beyond. So if you want to have the precise addresses, you have to reset it first and then get your samples where you want them. With the forward and reverse and the changing of the clock frequency, you can get extremely precise at your starting and stopping of sounds before jotting down your addresses, which could be used in a later project to reference in a program. Now what if we have an EPROM that just has data on it, i.e. program data, and we want to know what it sounds like? Well, obviously we don't always have to have audio on an EPROM. You could just take an EPROM out of a device that has data and that is the sound of digital data. Here's one of my personal favorites.
Mind the gap, mind the gap, mind the gap, mind the gap.
If you're wondering where I got the case, many of you out there have probably heard of a company called Johnson Controls, which does air conditioning control systems. Well, one time at a job where I was doing air conditioning controls, mind you, Schneider Electric, thank you very much, not Johnson Controls, we were replacing an antiquated 1994 vintage Johnson Controls control system with a modern and a much superior Schneider Electric system. And the old control system had 3 of these cases as part of the main control center. 2 of them contained a transformer, and the other one was, I think, just some wiring. So these cases are great. I've taken the transformers out and used them in for a power supply, but they're great cases. They're easy to take the front cover off. They have a nice aesthetic look to them. And you can see this vent right here. I have a 3 by, is it 5 inches, 6 inches speaker that fits perfectly in this area. Perfectly. And that was the inspiration to use this case, because it looks like it wants a speaker with that vent there. It fit the speaker so perfectly in there. And with that, it's the rest of the thing being just blank on the front makes it a very, very nice project case. Here I have some blank proms that I want to program. They can only be programmed once. Here I have an EPROM programmer. Here is the software for said programmer. I decided I want to capture this experience because only at rare times do I ever program a prom, considering the fact that they can only be programmed once. The prom has been loaded onto the EPROM programmer. Here you can see the IC on the programmer. Now we'll program the prom. First, we verify that the data that we want to put on the prom is the correct data. I'm going to go ahead and do a blank check. Device is not blank. It looks blank to me. Well, we'll try. Maybe it's expecting zeros. So, it's expecting zeros. Make sure that's in there good. Blank check complete, read. It's zeros. So as you can see, before I was not making good contact on there. But this programmer, although it normally detects whether you have poor contact on a pin, apparently that check does not work for a prom. It works for EPROMs though. So now that I've got confirmed reading a blank state, which is all zeros for a prom, do a blank check one more time. We will load the desired data. We will make sure the desired data is there. Then we will program the prom. Oh man, here we go. You can only do it once. Oh, it's programmed now. That was quick. Read. Go back to edit. You can see the data is there. That prom has been programmed. The prom will be removed from the programmer. I must redact what I said about it detecting poor contact on proms. I guess the earlier prom where it was reading as FF, there was poor contact on one of the pins, but it did not detect it as poor contact. But obviously on some other pin it does detect poor contact right here. But sometimes if that happens, I gotta kind of just wiggle that around a little bit and kind of re-put it back in there. And we'll try it, retry. There, blank check complete. If I read it, we should have all zeros. Blank check complete. Load the desired data. Edit, make sure we have the desired data in there, and program. Verify. Here's the address finder before hooking it up to the EPROM player. And this, you can see it's got 5 chips in there. The idea is to take 4-bit binary and show the hexadecimal on the 7-segment display. The problem, of course, being that I don't have any chips on hand that did that by default. I have BCD, you know, 4-bit binary to BCD, but it will only go to 9. So to have the hex, I used a form of programmable read-only, or I used some programmable read-only memory chips. Some old chips called the 82S123, which I actually have a bunch of, blank ones, and I programmed them with the appropriate data to do hexadecimal displaying on a 7-segment display. Just want to show what it looks like inside the display portion before I put this together. Here's the prototype of the project. So basically on this project here, the EPROM player, we have a 555, or in this case a 7555. I think a regular 555 will work too. Timer chip to provide the clock. Here is a reset button, which simply goes to the clear pin on all the counters. The clear pin is connected on all the counters together so that whenever I give it a high signal, 5 volts, it will reset. I have a switch here to switch between continuous play or hold down button to play mode. This button is debounced. It's a normally closed and normally open push button. Debounced, which I will show the schematic for shortly. And through another gate, it's basically when you hold it down, it goes to an AND gate, which allows the clock to go through only whenever this is held down. But when the switch went to the other position, it just has a clock go directly. Then this switch switches between the count up and count down, receiving the clock. If whatever clock pin of the counter is not used, is going to be tied high through a 10k ohm resistor. But whenever one of them receives a clock, it'll count up or down depending on the count up or count down receiving a clock. So of course it's counting up now, playing forwards, but I can also change the direction and make it count down and play in reverse. So I have 5 4-bit presettable counters here, and I have 5 of them so I can get up to 20 address lines to have enough addresses for the 27C080 EPROM, which is 8 megabits or 1 megabyte. Now, since various different EPROMs have different configurations on which pin receives the power, which pin is an address line, or whether it's a program line, or this or that, I have a selector switch that selects the different EPROM types. And I have those outputs simply going to address lines of a 2716, who are all tied low through 10 kilo ohm resistors. So whichever one is high, which it will determine through logic that is just being done through read-only memory to save from having a bunch of chips, the data lines will control whether it's receiving an address or whether it's receiving a constant 5 volts or constant 0 volts. And I have little transistor circuits here, which I'll show in the schematic soon, to provide more oomph, to give enough power to power EPROM if it goes to a power pin, because this EPROM's output does not provide enough current to be able to power up the actual EPROM the sound plays from. So obviously this EPROM here, a 2716, has combinational logic implemented in read-only memory. This EPROM here is the one the sound plays from. Right here we have a digital to analog converter, and the output of that goes to a Sallen key low-pass filter, I think it's a third order filter, but it has 2 critical frequencies that can be adjusted with these trimmers. This is recorded with a very low sampling rate, so whenever I don't have the trimmers, or whenever I don't have the filtering, there's lots of aliasing. So I have to turn those down or turn up the filtering. Then I have an LM386 audio amplifier, though right now I'm tapping off before the amplifier to an external amplifier. But anyway, that's basically how the circuit is breadboarded on here, and I just wanted to document what it looks like before I disassemble it. Now I have a 6-position rotary switch and an external switch here to switch the first set of 6 or the last set of 6 where only 4 are being used on that last set. I have a 12-position rotary switch on the final device, and so I'm implementing whatever is normally done with this switch just through diode logic. Because I didn't want to use this 6-position rotary switch in the project, ultimately I was going to see if I had another 6-position rotary, but I didn't have a smaller 6-position rotary, or one like this one. But I had a bunch of 12-position rotaries, so I used a 12-position rotary in the final device. I want to document what this looks like and everything before I disassemble the breadboarded circuitry. So it's a pretty fun project. Take note that the NAND gate I used here is not a 7400, it's a 74C100 or 74C00, and the counters I used here are not 74193s, they're 74HC193s. If you want to build this yourself, keep that in mind, because I tried using 74, I think, LS 193s and they did not work. I tried using a 7400, and although the debounce worked, the continuous or push button selecting did not work. I had to use CMOS parts and then it worked. And there's the DAC, a filter, I think that's just a buffering transistor there, and then the amplifier there with the 386. So anyway, that's basically what this is like, and I'll be showing schematics after this for this EPROM player project. I at one point had just one 7-segment display on the breadboard, which I have since removed to put in the project, as well as the PROM that I had programmed. I removed it to put it in the project as well. Okay, the schematics for this EPROM player are drawn in several different parts. First, I will show the pinout for the counter chip. I used 74HC193s. These are 4-bit presettable up-down counters. You can see QA, QB, QC, and QD are the data outputs, QA being the least significant bit. Data B in, data A in, data C, and D in are data inputs. When the load line is made low, the device can be presetted with a preset count, i.e., as long as load is held low, the data inputs are equal to the data outputs are equal to the data inputs. When load goes high, the data outputs will stay at whatever the data inputs were the moment it went high. To count up, you put the clock signal on count up while count down is held high. Vice versa, when you want to count down, you put the clock on count down while count up is held high. If you want to cascade counters, the count up of one counter goes to the, or excuse me, the carry out of one counter goes to the count up of the next counter, and the borrow out of one counter goes to the count down of the next counter. So they're cascaded like that, with the least significant nibble, or 4 bits, counter receiving the clock signal. It is a schematic basically for the counters. It's simplified. I didn't put all the pin numbers on the 74HC193s, and I didn't write down the power and the ground and VCC, but as on the previous pinout, those can be easily seen. But you can see that I have 10 kilo ohm pull-up resistors for the count up and down, so that if the clock is only going to the count up, the other side is pulled up. And the carry out goes to the count up on the next counter, and the borrow out goes to the count down on the next counter, and then there's 5 of these is all connected together. All the clears are hooked up together. There's a pull down resistor, and whenever you press the reset button, it just puts 5 volts onto the clear. Then on the DB25 connector on the side, there's a pull-up resistor there, and if you put a low signal on here, it will make load low, otherwise load is high. All the data inputs of the chip go to the external connections on the DB25 connector, and the data outputs go to the address lines of the EPROM, except there are a few that go to a different EPROM, as you'll see soon. Here is the clock, which is a basic 555 timer circuit with a wide range of adjustment using a 2 mega ohm pot. Now the clock switching is done in a certain way. To switch the clock, the output of the 555 can either be directly connected through this selector switch to go to either the count up or to the count down, depending on that selector switch, or if the selector switch is in this other position, it goes to this NAND gate, which receives the clock, and if this NAND gate receives a high signal here, an inverse of the clock will appear right here. Now, whether the clock is inverted or not doesn't really matter. It's just going to be a clock signal to play the audio, and the audio will still play. So I didn't bother inverting it back afterwards. Now the play button signal could just go to the button by itself, but if I did that, it wouldn't be debounced, and it would jump too many times. So I put a debouncer circuit on, which is using 2 other NAND gates with a normally closed / normally open push button. And it's hooked up like this, and using this circuit, this output here is a debounced, a very clean debounced signal from the start-stop switch that you hold down to play. That debounced output signal is the play button signal here. Now you'll see an EPROM right here at 2716. This is not the EPROM you're playing sound from. This is an EPROM that has combinational logic implemented in read-only memory. Because of the various different pins of some different types of EPROMs, some of them, sometimes it's power, and sometimes it's an address line, or sometimes it's always high, or sometimes it's always low, I did switching through the EPROM. I had originally used a 6-position selector switch and was going to use a separate switch to switch either one set of 6 or a second set of 6. Except in the second set I was only using 4. The reason why is because I was selecting between 2716 or 2732 or 27128 or 27256 or 512 or 010 or 020 or 040 or 080 or 10 different chips. So I'm only using 10 positions of the selector switch, or in this case I was going to use 6 positions, or if that switch was on, for the first 4 positions. But because I only had one small 6-position selector switch, and I had a bunch of 12-position selector switches, I ultimately put a 12-position selector switch in the final device. Using this arrangement of diodes, I was able to get positions 7 through 10 to be the equivalent of turning this switch on with having the first 4 positions. How I did that was through positions 7 through 10 would give a diode that would go to the same connection as position 1, so that address of that EPROM would still receive that signal, and it also went to a diode to go over here to go to address 6 of the 2716, which is right here, which used to go to this little switch here. So that's the diode arrangement, taking care of a 12, so I could use a 12-position switch here instead of a 6. Of course, the first 6 positions are still hooked up in the same manner with 10 kilo ohm pull down resistors, and the first 6 address lines of the chip, the 7th address line, or A6, since we're starting from 0 here, is the output of this diode arrangement. These last 4 address lines of the 2716 go to a 13, 14, 17, and 18. Now these A13, 14, 17, and 18 address lines are the outputs from the counters that would have otherwise gone to the address lines of the audio chip. Instead, those address lines coming from the counters that count through the addresses go to these parts. And then from the logic inside, depending on what chip is selected, you'll get the address lines here. The pin 31, pin 30, pin 29, and pin 28 here refer to pins that would be on a 32-pin chip in the ZIF socket, but will still work with pin chips that have less pins, such as 24 or 28 pin chips that are seated where they are on the bottommost portion of the ZIF socket. They will still match up. Because I can't power a chip directly off of this EPROM, in any instances I wanted to power a chip, I used a PNP transistor here, which meant I had to give out a low in order for this to give out a high. Now, we've seen that. Let's look at the digital to analog. So the data lines off of the audio EPROM go straight to an AD558 DAC, or digital analog converter. Chip select and chip enable are always tied low because we're always using the chip. And then the voltage output, as well as the sense and select, those pins there, 14, 15, and 16, are all tied as the audio out, which go to our Salin key low pass filter. With these values, I get a very wide range of critical frequency control. I think the lowest critical frequency is somewhere in the neighborhood of 700-ish hertz or so. And the highest critical frequency is, I think, around 30-something kilohertz or something. So you're basically going to be able to get a very wide range that covers no low-pass filtering at all to low-pass filtering so low that you could have a sampling rate as low as 2 kilohertz and still be able to low-pass filter it good. From that filter, It then goes on into a basic LM386 audio amplifier with an important decoupling capacitor here and an important decoupling capacitor here to get rid of any DC components. If you do not have this 1 microfarad cap, you'll be putting DC into the amplifier, which is just going to make it go to the positive rail voltage extremely easily and make clipped, very distorted sound. And if you don't have this capacitor here, you'll also be putting DC into the speaker, which you don't want to do. So you want those decoupling capacitors. I have an audio output jack tapped off the filter, but before the volume control, so I can get a line output that I can feed into an external amplifier or recording device. The power supply is very straightforward with your step-down transformer, rectifier, filter cap, a 7805 5-volt regulator, which goes to all the logic, including the DAC and including the filter. But then I put a 7812 voltage regulator for the audio amplifier so I could turn it up a little louder before it clips. That is the basic ways of operation of this. Obviously this is probably going to cause a lot of confusion, but basically it's just switching. And I think some of these settings ended up being redundant anyway. A lot of them ended up being. I use this guide here because all the chips are all seated on the bottom and most of these pins are all the same. These crossed out ones I'm not using. But most of the pins are the same, and I didn't change any of the pins on this side, though I have bad news. That is a 2764 you want VPP to be tied high in order to be able to get the data out of it. On a 27C64, the VPP doesn't matter. I had the VPP low and it was just fine. I was able to play sound out of a 27C64. But when I tried a 2764 without the C, it wants VPP to be high, otherwise it won't play any sound, which meant I had to change the knob to a larger sized EPROM selection, and then once the address 15 line went high, then it started playing sound out of a 2764. That is a design flaw in this, but after finding out the fact, I had already had the device together and I didn't want to get a bigger EPROM with another address line and redo all the logic and everything just for that. And I don't use 2764s for PCM sound very much, and if I do, I just use a 27C64. Anyway, I have a bunch of those, a ton of 27C64s lying around, believe me. So I'll just stick to the 27C64. But the only switching I do is these pins here. 31, 30, 29, and 28. Of course, shown of being on a 32 pin chip. Obviously, you'll see 28 is a power pin on the 24 pin chip, and 30 is a power pin on a 28 pin chip, and that is why I'm using these transistors here so that I can give power to the chip when needed. Otherwise, if it's just an address line, you'll still get your logic. I just got to make sure that whatever the address line coming into this 2716 here is going to have its value inverted coming out if it's the one that I have selected over here. Anyway, that is the schematic showing. Sorry that it's in so many pieces. The schematic showing, oh, I'm not done yet. I thought I was. The address finder. The address finder is pretty simple. But the address finder, I wanted to show hexadecimal. So all the address lines, these are coming out straight out of the counters. This is ignoring this weird chip selection thing I have here. This is before that. This is the address lines coming straight out of the counters. I just showed 1 nibbles worth or 4 bits worth, but this of course is going to be multiplied by 5. Each counter is hooked up to an 82S123. Now this is one of those chips that I don't even sure they make them anymore. I don't think they make them anymore. To find new old stock of these online, you might be expected to pay a decent amount of money just for one of these chips. It is a EPROM, or programmable read-only memory. It has a astounding 32 bytes of data storage, and you can only program them one time because they're actually blowing microscopic fuses inside the silicon when you program the bits. So yeah, I had a bunch of blank ones. I have a whole bunch of blank 82S123s, so I used 5 of these to convert them into 4-bit binary to hexadecimal converters for a 7-segment display. Since the other chips that I had lying around for 7-segment displays are only BCD, I wanted to show hex, so I used the EPROM chips to do that. So anyway, that's that.
I come from EPROM, yes you know it's true. I come from EPROM, yes you know it's true. I come from EPROM, yes you know it's true. I come from EPROM, yes you know it's true. I come from EPROM, yes you know it's true. I come from read-only memory, like in a computer. I come from read-only memory, like in a computer. It's masked. Oh man, it's masked freaking wrong, coming at you live. You can't change my program at all. I am masked wrong. You can't change my program at all. I am masked wrong. Masked wrong, yeah! Masked wrong, yeah! Masked wrong, masked wrong, masked wrong.
Get ready for computer action. Just saying. Computers, you'll always find out. Computers, you'll always see everywhere. Technology has taken the world by surprise. Technology has really got the world in a grip. Technology will always amaze you with its ways. Technology will always distract you on the internet.
Viewers, I hope you enjoyed this video on the Eeprom player project, as well as the 1000th video celebration for the CassetteMaster YouTube account. Counting 1,000 public videos now on my channel. That's quite a number of videos. I first started this YouTube channel on the 28th of January 2007, and I'm still uploading videos 12 years later. Anyway, although I don't ask normally for these things, I would appreciate any more likes and subscriptions and all that kind of stuff. Well, I don't think this channel gets very many views at all, which really doesn't come as a surprise to me, honestly. But anyway, my camera's trying to turn off on me, but I hope you enjoyed this video.